Assalamualaikum warahmatullahi taala wabarakatuh, and very good day to all my beloved students. This time, sir will show you how to solve the problem related to the open system or control volume. Hope this tutorial or exercise can assist you to answer the rest of the question related to the open system. This is the question selected for this tutorial. Air enters an adiabatic nozzle steadily at 300 kilopascal, 200 degrees Celsius, and 30 meter per second, and leave at 100 kilopascal and 180 meter per second. The inlet area of the nozzle is 80 centimeter square. Determine the mass flow rate through the nozzle, exit temperature of the air, and exit area of the nozzle. While you are getting this question, there are few important remarks you need to capture. Firstly, air, okay, meaning that we will use the ideal gas equation. Adiabatic, meaning that Q equal to 0. Nozzle is the device that we use for this question. Steadily, meaning that the delta T equal to 0 or no change with time. The rest is the 3 kilopascal, 200 degrees Celsius, 30 meter per second as a part of the entering to the nozzle. And then for the leaving from the nozzle, 100 kilopascal with velocity 180 meter per second. Also, you will be informed inlet area, which is another information related to the entering nozzle, which is 80 centimeter square. And then you will ask mass flow rate. So just remember, the nozzle will experience same mass flow rate, either inlet or outlet area. Exit temperature, meaning that T2, and then exit area of the nozzle, which is A2. Step 1, sketch and extract data on the nozzle diagram. In the form of sketch, you may go for a very rough sketching. Okay, and extract data means that, let's say this one is the entering part and this one is the leaving part from the nozzle, and try to list down all the information related to the enter of the system. For this case, it's nozzle, and try to list down what is the information related to the exit or leaving nozzle. And then obtain the specific volume and mass flow rate using ideal gas equation and mass flow rate equation, which apply the specific volume information. This is the equation. PV equal RT for the ideal gas equation, and this is the mass flow rate equation, which is m dot equal 1 over V A times V. And third step, use energy balance equation to obtain temperature at state 2 by using the energy in equal to the energy out. And finally, step 4, apply the ideal gas equation and mass flow equation to determine area at state 2 or at the exit nozzle by using the same equation. Step 1, sketch and extract the data on the nozzle diagram. This is the sketching data for the nozzle. So air refer to the properties that entering the system. 1 refer to the enter or in. 2 refer to the leaving or exit. And we list the information from the question, the P1. 1 refer to the 1 inlet, okay, or enter. V, temperature and area for 1. And then we list out as well the outlet P2, V2 from the question, and we need to determine T2, A2, temperature 2 and area 2. we are given as well to determine uh, mass flow rate. Bear in your mind, the mass flow rate for nozzle should be same for inlet and outlet due to the one single stream for this nozzle. And do not forget to list out the simplification, the assumption or the simplification. Adiabatic Q equal to 0, no work equal to 0, steady state in the form of the delta T, no change with time, no potential energy information, and statement, ideal gas with constant specific heat. Step 2, obtain the specific volume and mass flow rate using ideal gas equation and mass flow rate equation which apply the specific volume information. We need to determine R or gas constant of air from table. We will show later. But before that, we need to use the equation of the ideal gas equation from the PV equal RT. And then we rearrange in the form of the specific volume and we get RT over P. And then we obtain the R, okay, the R by referring to the property table, and we look for the substance of air since the question asks for air, and then we go straight away to refer the table gas constant R kg per kilogram Kelvin, which 0.287, and then we just insert all the information. For example, this R for this ideal gas constant and temperature 473 Kelvin, noting that the 473 Kelvin come from 200 degrees C plus 273. It is the conversion from the Celsius to the Kelvin. And then the P1, 300 kilopascal. And finally, we get the answer for specific volume 0.4525 meter cube per kilogram. After that, we use the mass flow rate equation and we insert all the information that we get from the previous calculation, specific volume, area, and also the velocity. And finally, we get the mass flow rate 0.5304 kilogram per second. Step 3. Use energy balance equation to obtain temperature H2 or at the area of a living nozzle. Using the energy balance equation, which energy in minus energy out equal to the rate of change in energy system over dt. But knowing from the question, it gives us the condition is the steady state or no change with time. So the delta E over dt is 0 and we can cancel it. And then we rearrange the equation, this equation to become this equation, which is energy in equal to the energy out in the form of heat, work, and mass for inlet, and heat, work, and mass for outlet. So the unit for the energy balance is kilowatt. After that, we expand the equation from the energy balance from E in equal to E out to become Q in, work in, and mass for inlet, and Q out, work out, and mass flow rate out for outlet. And then we substitute the data using this equation: enthalpy, kinetic energy, potential energy, and finally we can get the full equation for the energy balance like this. Q in, W in, M dot or mass flow rate. So this is the theta. Okay, so this is the theta. Same goes to this one, theta at the outlet region. We just substitute the theta in the energy balance equation. After that, after we insert the theta to replace with the H, with the kinetic energy and potential energy, we rearrange the equation, the energy balance equation, which Q and W we put on our left hand side, while the others we put on our right hand side. But we still categorize for the energy for the exit and the energy from the inlet. And then we try to rewrite this equation in this form. Q minus W, mass flow rate, enthalpy, kinetic energy, and potential energy. So by having this equation, so you guys need to remember this governing equation related to the open system. It can be applied to the others application, not only for the nozzle, but also go for the diffuser, compressor, or turbine. But also, you need to consider from the question given. For example, let's say the question do not give us any information related to the work, meaning that we can cancel out work. For example, as well, let's say the question mentioned the system is adiabatic or Q equal to 0, so that we can cancel the Q. So those information will simplify our equation based on the problem given. So that's why we need to understand or to remember this equation. Then we try to apply accordingly to the problem statement given in the question. Step 3, use energy balance equation to obtain temperature at state 2. We continue to obtain the temperature at state 2 by using the governing equation for the open system. But based on the question, we obtain this information so that it can assist us to simplify the equation. So have a look. So Q equal to the 0, for example, equal to 0 because the system mentioned that the system is adiabatic, Q equal to 0. And same goes to the no work, meaning that work equal to 0. Steady state mean we already used this information for the energy balance equation, which is delta T equal to 0, no change with time, so that energy in equal to the energy out. And then of course the potential energy, do not any mention related to the potential energy, so that we cancel out the potential energy part. And yet they mention about the ideal gas with constant specific heat, which is we will replace the enthalpy to the specific heat for the ideal gas condition. So this is the equation after the simplification by putting all the value in the form of 0, and then we get this equation. And then since the question mentioned about the gas, meaning that the enthalpy need to change from the H symbol or H unit to become the Cp over delta T. And then we just replace this equation to be inserted in this equation, and finally it will become this form. Okay, so how to determine the Cp? We just refer to the table for Cp, kilojoule kilogram Kelvin, and then pick the equation, pick the temperature 450 equal to 1.020 kilojoule per kilogram Kelvin. Noting that 450 is not the exact value, because when we add 200 Kelvin, sorry, 200 Celsius plus 273, it will become 473. Okay, it's not 450. But since notice that the value for the CP is not much different between the 450 and 473, so directly choose 1.02 as a CP. But if you want to do the interpolation to obtain the exact figure for the temperature 473 Kelvin, you may go, and that is not wrong, because Sir already calculate, and we obtain the 473 is more or less than 1.024, which is different from the 540 Kelvin, and 437 Kelvin is 0.004, which is very small. So that's why Sir only just take this 540 Kelvin as a CP value 1.02, because the difference between the 473 is relatively very small. But if you want to do the interpolation, you may go ahead. There's nothing wrong with that. And then after that, insert all information in energy balance equation to obtain temperature at state 2. We're still using the previous equation, considering the CP average times delta T, and this is the kinetic energy. And then we just insert all the information. This is the kinetic energy. Okay, so this is the CP delta T. So this is the conversion from the joule to the kilojoule for kinetic energy. Let's explain this one. Knowing that the velocity power of 2 equal to the meter square per second square, which refer to the unit of joule per kilogram. But from the CP equation, we're using the kilojoule per kilogram. So to convert the joule per kilogram, so we need to divide by 1000 to become kilojoule per kilogram. Okay, it's just the 1000 refer to the conversion from the joule to the kilojoule for the kinetic energy. And then finally we obtain the final more or less 184.6 degrees Celsius. Step 4, which is the final step, apply the gas ideal equation, mass flow rate equation to determine area at state 2 or exit of nozzle. So using the same equation, PV equal RT, and then rearrange the PV RT in the form of the specific volume and determine RT2 P2, which is this the ideal gas constant, this the temperature. We convert from the Celsius by add 273 to become Kelvin, and then P2 100 kilopascal, and finally we obtain the specific volume is 1.313 meter cube per kilogram. Next, we apply the mass flow rate equation and insert all the information related to the mass flow rate, the specific volume, and the velocity. And finally, we get the area at the exit nozzle, 38.7 centimeter square. We can cross-check our answer by list down all the information related to the inlet and also to the outlet. We check at the area. For the area to or the exit is 38.7, which is lesser than the A1 or area 1, 80 centimeter square, meaning that we are answering in a logic manner in the form of the characteristic of the nozzle. Same goes to the velocity from the equation. It will give us for the V1 30 meter per second only, but for the V2 or the exit nozzle 180 meter per second, which is according to the characteristic of the nozzle. So that is the important remark. So want you guys to understand, because it can assist you to cross-check your final answer from the given problem or situation. This is the question. So hope you guys can try this during your free time. The question more or less the same, just the matter changing a little bit of data or figure related to the cases. But the question so provide the final answer A, B, and C. Hope you can try to do this by your own and refer to the step by step from the video. Hopefully you get the benefit from this exercise. Assalamualaikum warahmatullahi taala wabarakatuh. Thank you.